Pluto, a far-off and confounding body, was once viewed as a solitary and real planet, an individual from our planetary family. However, ongoing, upsetting verbalizations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an amazing disclosure. They proposed that this cold world is on a potential impact course with Neptune. But how is it that this could work out? Furthermore, what may be the results of such a giant event? Are we seeing an entrancing influence caprice? Or is there something else to this oncoming boundless episode? Go along with us as we investigate the potential results of a Pluto-Neptune impact. Pluto, a previous planet that was consigned to a more unobtrusive status, remains a subject of interest and study in the grandiose community. According to tenacious figures by leading specialists, Pluto's circle is perilously near Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are raising the alarm about a possibly perilous calamity between these two planets, which could represent a critical danger to Earth. But how is such an event even conceivable? Pluto's circle around the Sun is surprising compared to some other planets in our close-by planetary framework. It takes a shocking 248 years to finish a single circle, which actually means that, since its discovery in 1930, it hasn't even completed one round trip. However, the interest doesn't stop there. Pluto's circle is described by its highly unconventional shape, altogether different from the almost round circles of the major planets. What makes Pluto's circle considerably more surprising is its tendency of 17 degrees to the ecliptic plane. The way Pluto follows is substantially more unpredictable compared to other planets. This tendency and anomaly add layers of intricacy to its orbital pattern. Maybe one of the most enthralling parts of Pluto's circle is its connection with Neptune's circle. For something like 20 years in each circle, Pluto actually draws nearer to the Sun than Neptune, in opposition to what we would anticipate from their positions in the planetary framework. This prompts the clear inquiry: why hasn't Pluto collided with Neptune? The answer lies in the gravitational impacts of other planets. The assessment of Pluto's circle started soon after its discovery. Initially, space specialists tried to make sense of its surprising way. Dissimilar to other planets, whose circles lie relatively near the ecliptic plane, Pluto's circle stood apart with its dangerous tendency and erratic shape. The secret surrounding Pluto's circle can be made sense of by the three-body issue in divine mechanics. This is tied in with understanding how three objects in space, like Pluto, Neptune, and the Sun, move and interact with each other through their gravitational forces. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this issue shows how its circle, Neptune's circle, and the Sun's gravity all communicate in a complicated manner. Terms like asymptotic libration, scope libration, and the VZK wobbling are essential for this riddle. According to astrophysicists, what's keeping all planets in their circles is a kind of libration. In the case of Pluto and Neptune, this term means that when Pluto crosses Neptune's circle, its position is generally something like 90 degrees away from Neptune. This spatial separation is essential in keeping their circles from influencing each other. Degree libration, on the other hand, refers to the vertical movement of a heavenly body in its circle. For Pluto, this suggests that when it comes closest to Neptune or some other giant planet, it is situated far above their orbital plane, adding an extra layer of protection from potential impacts. One more critical element in this present circumstance is the VZK wobbling, named after three researchers, VA, LV, and KU, who studied how objects move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling influences how they move. For Pluto's case, the VZK wobbling helps us understand why its way close to the Sun is so unusual. Despite the apparent randomness, this influence helps keep Pluto's circle stable for an incredibly long period of time. The VZK wobbling shows that, despite the fact that things in space could appear to be turbulent and conflicting, specific patterns and forces help keep everything under control. These elements help safeguard Pluto's circle, ensuring it doesn't collide with Neptune or drift off course. This three-body issue influences how we grasp these circles, especially in how space objects pull on each other. Focusing on this helps us concentrate on Pluto, our adjoining planetary framework, and far-off stars and planets. Mathematical simulations in the late 1980s revealed that, regardless of these unpredictable properties, Pluto's circle is still stable, with little deviations in initial conditions leading to significant differences over extended periods. However, these bizarre qualities of Pluto's circle have been found to maintain consistency over incredibly long timescales. Later computer models have assisted us in understanding how the giant planets, like Neptune, Jupiter, and Saturn, impact Pluto's circle around the Sun. Neptune has an interesting relationship with Pluto, where for every 2 circles Pluto finishes around the Sun, Neptune finishes 3. This resonance helps keep Pluto's circle stable. However, Neptune isn't the only component. Jupiter's gravity also plays a significant role in defending Pluto's circle, and Saturn also helps in that expansive region. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a steady course for an incredibly long time, potentially even billions of years. Maybe Neptune, Jupiter, and Saturn are cooperating to ensure Pluto can keep circling securely in space without running into trouble. These abnormalities are essential in the larger context of the universe, for maintaining the strength and consistency of divine bodies. Without these factors, our nearby planetary framework, as we probably know it, would be a place of far greater unrest and instability. Bodies like Pluto could, for sure, collide with others or be shot out from their steady circles, setting off a cascading impact on other heavenly bodies. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its circle is critical. This gives us a clearer picture of the dynamic nature of adjoining planetary systems. The case of Pluto shows how, even in the most evidently unstable circles, an equilibrium can be accomplished through the complex cooperation of gravitational forces and orbital mechanics. It also highlights the importance of consistent observation and analysis of these abnormalities to better handle our place in the universe. Investigating the depths of space frequently leads us to confront the unusual nature of heavenly bodies. Furthermore, Pluto's circle is an ideal model of this unusualness. The possibility of orbital resonance, which suggests the fragile reliance of a divine body's circle on its initial conditions, is clearly demonstrated. For Pluto's case, this means that even slight changes in the dwarf planet's position or speed can significantly change its long-term circle. Using virtual simulations has been crucial for exploration to figure out how Pluto moves in space. These models use complex mathematics to recreate how Pluto, alongside other space objects like Neptune, pull on each other. By modifying small details in the simulations, astronomers can observe how even minor changes can have a huge effect on where Pluto ends up. In the late 1980s, these simulations uncovered something very interesting about Pluto's circle. Despite having systems like asymptotic libration and expansion libration to stabilize it, its circle can still be astonishingly inconsistent. If you start with even a slight difference in where Pluto is or how fast it's moving, over many years, its path could end up looking entirely different. Despite this turmoil, Pluto's circle remains stable for billions of years. This suggests that Pluto's journey around the Sun has a certain order to it, even though it seems tumultuous at first, particularly when it involves erratic circles like Pluto's. This presents tremendous challenges. The inherent nature of these systems suggests that long-term forecasts are often filled with uncertainties. While mathematical simulations are an essential tool for understanding and predicting the future behavior of divine bodies, they also highlight the limitations of our predictions. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or deviation can drastically change the outcomes, making exact predictions exceedingly difficult. Moreover, the turbulent nature of large circles like Pluto's serves as a reminder of the ever-changing and dynamic nature of the universe. While we've made tremendous steps in understanding space, Pluto's model helps us to remember how our comprehension of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's circle offers significant insights into the broader dynamics of the nearby solar system. It shows how the presence and position of each planet can have sweeping consequences for the stability and direction of other bodies within the system. So why are prominent astrophysicists suddenly raising concerns about a possible impact between Pluto and Neptune, regardless of all these intricate forces trying to prevent such an event? Neil deGrasse Tyson, a popular astrophysicist, offers a book-length perspective on the mysteries of our nearby solar system, especially the captivating example of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of divine mechanics and the public's interest in the overlooked corners of space. His position on Pluto's renaming is framed in the ever-expanding knowledge of our solar system. He views the renaming not as a diminishment, but as an important change in agreement with our growing understanding of the many bodies surrounding our Sun. Tyson's approach to divine mechanics is one of constant learning and change. He views the complexity of Pluto's circle, as well as its interactions with Neptune, from a perspective that acknowledges the unpredictability of space. He suggests that while Pluto's circle is stable for now, it could undergo tremendous changes in the future. This possibility serves as a reminder of how much we still have to discover about the forces shaping our planetary system. In the grand scheme of things, Pluto's circle is a captivating case study in the complicated interplay of gravitational forces within our nearby solar system. While its circle is stable right now, the mysterious elements between Pluto, Neptune, and the other planets suggest that even the most apparently stable circles could change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the mysteries of the universe, they help us better understand the delicate equilibrium that governs the movements of heavenly bodies. The potential for a Pluto-Neptune crash isn't necessarily unavoidable, but it serves as a reminder of the constantly evolving and complex nature of the universe. Regardless of the established theories surrounding Pluto's circle, it's important to consider the broader implications of these forces for how we understand the nearby solar system and the universe at large. While Pluto's journey is one of intrigue, it is also a reminder that the universe is filled with mysteries and complexities ready to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a central piece of the riddle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is an essential part of divine mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that, despite their orbits crossing, the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic impacts. The importance of resonance in maintaining stability cannot be overstated. It provides a great example of how systems in space, even those that initially seem chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its irregular orbit, has remained stable for billions of years. This dynamic is a crucial part of the larger design of the nearby planetary system. The effects of planets like Jupiter, Saturn, and even Uranus are vital in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its massive gravitational power, acts as a sort of guardian for the interplanetary system, influencing the orbits of various asteroids and dwarf planets, including Pluto. In fact, some specialists speculate that Jupiter's gravity could have prevented Pluto from being ejected from the nearby solar system entirely.